Okay, in the previous video we had a brief introduction to rotational motion, and in this video we're going to first begin by looking at a formal definition of rotational motion. So this is the formal definition of a rotational motion. If each particle of the body moves in a circle and the centers of all the circles lie on a straight line called the axis of rotation, the body is said to be performing rotational motion. So let us see what this actually means. So let us say if this is an object which is performing rotational motion, and let us say this is the axis of rotation, this is the center, right? Okay, and this is the axis of rotation. Right? Now if I look at any particular particle in this, right, or I can draw a circle, right, which is this could be one circle, right, which is a part of this particular body. If I take any particular point on this circle, then and the center of this circle will lie on this axis of rotation. If I take a smaller circle, for example, again the center will lie on this circle. If I take a circle at a lower level, then the center will lie over here. So the centers of all the circles are lying on this particular perpendicular line, which is known as the axis of rotation, right? So if each particle is performing is moving along a circle and the center of the circle lies on one line, then we call it rotational motion. The other point to note over here is that this axis of rotation need not be in the center, right? It could be off, it could be over here here as well, right? For example, or let me draw another diagram, right? Let's say this is an object and the center of axis could be this. So it's kind of performing a rotational motion around this. So the axis of rotation can be anywhere, it could be in the center, it could be passing through the geometric center, or may not be passing. So that is what rotational motion is. The question that we are now going to look at is how and why is this rotational motion caused? Quite obviously, the body performs rotational motion because of application of force. So a force is being applied on this body and therefore it performs rotational motion. And when on application of force, a body performs rotational motion, we say a torque has been applied, right? Or moment of force, right? Torque or moment of force, right? And we will denote torque by T. Now, what is this torque? Let me once again write the formal definition of torque. Torque due to a force, right? The torque due to a force is the turning effect. It is the turning effect of the force about a fixed axis, which is the axis of rotation, right? And it is measured by the product of the magnitude of the force right? It is the magnitude is the product of the magnitude of the force. So it is a product of the magnitude of the force 1 and the perpendicular distance between the line of action of the force and the axis of rotation. The reason why I have taken the trouble of writing the entire definition is because I want to draw your attention to this definition very closely, so that we are able to understand torque and calculate or find out torque when we are given a situation. So let's go through this definition closely. Turning effect of the force about a fixed axis, and is measured by the product of magnitude of the force. So if I want to calculate the magnitude of the torque being applied, I have to take the product of the magnitude of the force and the perpendicular distance between the line of action of force and the axis of rotation, right? So I have to take the perpendicular distance, that means the shortest distance between the line of action of force. So if a force is being applied, say for example in this particular direction, then this becomes the line of action of force, because the force is being applied along this line, and I have to take the shortest distance between the axis of rotation. So if this is the axis of rotation, what is the shortest distance between this? So this is the perpendicular line, this is the line of action of rotation, and what I draw is from the axis of rotation. If I draw a perpendicular from the line of action of rotation and this line, then I get the shortest distance between the line of action of force and axis of rotation. When we calculate torque, we will look at this more closely, right? We'll take an actual example and find out the torque, right? So I want to once again kind of stress on the distance. The distance is between the line of action of force and the axis of rotation, right? Let's move on, right? And let us take an actual example to find out, get an expression for torque in the Cartesian coordinate system. So what we're going to do now is we're going to get an expression for torque in the Cartesian coordinate system. So let us draw the Cartesian coordinate system. Let us say this is the y-axis and this is the x-axis, and let us say one of the particles is over here and the force is being applied and it is performing rotational motion, right? And it is performing rotational motion along this particular circle. Let us say this is the circle around which it is performing rotational motion, right? Let us call this as point P, and let us say the force being applied on this particular is in this particular direction. So we are not taking force parallel to this or perpendicular, we are taking a general direction of force. Let us say this is the direction of the force, right? And this is the initial location, this is the position vector of the particle at some point t, and this is theta. And let us say after time t, due to this application of force, the particle reaches, say for example over here, let us say this is q, and now this becomes the position vector of the particle, right? So this is the force applied on this particle, this which is causing this particle to perform rotational motion, right? Please note that this particle is one of the particles of an entire body, right? Now how do we get an expression for the torque? How do we calculate the torque, right? This particular particle is moving around this axis of rotation. So I hope you're able to imagine the axis of rotation. It is exactly perpendicular over here. So you can imagine a line, right? Imagine a line which is going into the plane of the page of the paper. So exactly perpendicular over here, right? Exactly like this, which is going into the plane of the paper, downwards and upwards out. So let us try to get an expression for the torque, right? We have earlier learned that anti-clockwise torques are taken as positive, clockwise torques are taken as negative, right? So we'll use this while we calculate this torque. Okay, let us take the coordinates. Let us say this is x, this distance is x, and let us say this distance is y, right? So these are the coordinates of the particle in the initial position, right? And due to application of force in time delta t, it moves to location q, and let us say this is delta theta. Now this particular force has two components, one, right? This is Fy and this is Fx, right? And these two forces are responsible for this rotational motion. So these are responsible for producing torque and then producing rotational motion. So I will calculate the torque produced by each of the forces, right? So torque is equal to torque produced by Fy and Fx. Let us begin with Fy, right? Fy is acting in this particular direction. So of course the location is over here, right? So the Fy is acting at this location and in this direction. So what is the torque produced by Fy? For that I have to take the magnitude of Fy and multiply it with the distance between the perpendicular distance between the line of action of force and the axis of rotation. So this, if I take it vertically downwards like this, this is the axis line of action of force. And what is the distance between the axis of rotation and the line of action of force? It is as you can very clearly see is x. So this will give me a torque Fy multiplied by x. Okay. And this is the axis of rotation. This is acting in the upward direction, so it's producing a anti-clockwise torque. So it will have a plus sign. What about Fx? Fx is acting in this direction. So this is the line of action of force. And what is the distance between the axis of rotation and line of action of force? As you can see very clearly, it's equal to y, right? And therefore, the torque that Fx produces is Fx into y. Right? This is the axis of rotation. This is the force. So it will produce a clockwise torque. And hence, I'll have to put a minus sign over here. And therefore, I get the expression for torque. Torque is equal to x Fy minus y Fx, right? So this is how I get the expression for torque in the Cartesian coordinate system. Okay, one more small discussion we will have in this video, and then maybe we'll discuss the expression for torque in the polar coordinate system in the next video. The other thing that I want to take up in this video is that work is force into displacement. In linear motion, work is force into displacement. So if for this very small displacement, delta W is equal to F into S. So for rotational motion, F gets replaced by torque. Right? In linear motion, force causes motion, whereas rotational motion is caused by torque. So force gets replaced by torque, and displacement is delta theta. Right? Displacement is delta theta. This force has caused it to displace through delta theta. So delta W is equal to tau into delta theta. This is another equation I get. And if I divide this by delta T throughout, then delta W upon delta T is equal to tau into delta theta by delta T. Delta W by delta T, you know, is power, instantaneous power in fact, and this will give me torque into delta theta by T. This is angular displacement time, so this will give me angular velocity omega. Right? So power is equal to torque into omega. And this formula looks very familiar. In the linear motion, we had power is equal to force into velocity. Right? Torque is the corresponding thing for force in rotational motion, and instead of linear velocity we have angular velocity. Therefore power is equal to torque into omega. So this is how we get the expression for torque and power for a force applied on a body which is causing rotational motion in the Cartesian coordinate system. In the next video we will look at the same thing. We'll try to get an expression for torque in the polar coordinate system. Thank you.